Good morning and welcome to Physics Friday. If you're new to this series, click on the link above to see the whole playlist. In the last video, I introduced the International System of Units. Today I'm going to show you how to work with numbers in scientific notation. Scientific notation is a way of writing numbers so that even if the number is very large, like the mass of a planet, or very small, like the mass of a subatomic particle, we don't have to write pages full of zeros to do our calculations. It's also good for keeping track of significant figures in calculations, but that's the topic of the next video. The basic idea behind scientific notation is that you can write any number as a decimal value between 1 and 10 multiplied by a power of 10. The power of 10 indicates how far to the right or left the decimal point has been moved from its position in the original number. For example, my car has a mass of 1,300 kilograms. To express this in scientific notation, we move the decimal point to the left until the value is at least 1 but less than 10. In this case, we move it 3 places to the left, and we get 1.3 times 10 to the 3 kilograms. The 3 in 10 to the power of 3 is called the exponent, and it indicates that we move the decimal point 3 places to the left. I've got a packet of sweetener that has a mass of 1 gram, or 0.001 kilograms. What's that in scientific notation? Well, we need to move the decimal point 3 places to the right. Moving it to the left gave us a positive exponent, so moving it to the right gives us a negative exponent, in this case, negative 3. So the result is 1 times 10 to the negative 3 kilograms. What about some really big and really small numbers? The mass of the Earth is 5 septillion 972 sextillion kilograms. That's 5972 and 21 zeros. To put that in scientific notation, we have to move the decimal point 24 places to the left, giving a result of 5.972 times 10 to the 24th power kilograms. It should be obvious at this point that for numbers this big, scientific notation is easier to work with. Let's look at a small number now. The mass of an electron is a decimal point followed by 30 zeros, then 9109 kilograms. To put that in scientific notation, we have to move the decimal point to the right 31 places. Moving the decimal point to the right gives us a negative exponent, and we end up with 9.109 times 10 to the negative 31 power kilograms. So for big numbers we get a positive exponent, and for small numbers we get a negative exponent. What about converting the other way? Suppose you have a number in scientific notation and you want to convert to an ordinary decimal. The rule is the same. For every place you move the decimal point to the left, add 1 to the exponent, and for every place you move it to the right, subtract 1 from the exponent. To make an ordinary decimal, we want an exponent of 0. So for example, a jet aircraft has an airspeed of 2 times 10 to the 2 meters per second. What's that as a decimal? Well, we want to reduce the exponent from 2 to 0. To do that, we have to move the decimal 2 places to the right. So moving it 1 place to the right, we get 20 times 10 to the 1 meters per second, and moving it another place to the right, we get 200 times 10 to the 0 meters per second. 10 to the 0 power means don't multiply at all, so we can leave it out of the equation, and we get 200 meters per second. The smallest viruses are about 2 times 10 to the minus 8 meters in length. What's this as a decimal? Again, we want to get the exponent from negative 8 to 0, so that means increasing it by 8, which means moving the decimal point 8 places to the left. This gives us 0.0000002 meters. Okay. Now that we know how to write numbers in scientific notation, how about adding, subtracting, multiplying, and dividing them? We'll start with multiplying since that's the easiest to do. To multiply numbers in scientific notation, we multiply the decimal parts normally, then add together the exponents. As an example, let's calculate the angular momentum of Earth orbiting the Sun. In this case, the angular momentum is the Earth's mass times its orbital speed times its distance to the Sun. This gives us 5.972 times 10 to the 24th kilograms times 3.0 times 10 to the 4th meters per second times 1.5 times 10 to the 11th meters. We multiply together the decimal parts, 5.972 times 3.0 times 1.5 equals 26.874. Then we add together the exponents, 24 plus 4 plus 11 equals 39, so we write times 10 to the 39. Then we multiply together the units, kilograms times meters per second times meters is kilograms times meters per second squared divided by seconds. So our result is 26.874 times 10 to the 39th power kilograms meters squared per second. Notice that the decimal part isn't between 1 and 10. To get proper scientific notation, we need to move the decimal point one more place to the left. Remember, when we move the decimal point to the left, we're increasing the exponent by 1 per place we move it. So our final result is going to be 2.6874 times 10 to the 40th kilograms meters squared per second. Dividing numbers in scientific notation is similar. We divide the decimal part and subtract the exponents. So if we wanted to find out how much more massive the Earth is than the Moon, we could divide the Earth's mass by the Moon's mass and get a ratio. 5.972 times 10 to the 24th kilograms divided by 7.348 times 10 to the 22 kilograms. We divide the decimal part, giving 5.972 divided by 7.348 equals 0.8127. Then we subtract the exponents. 24 minus 22 equals 2, so we write 10 to the 2. The kilograms cancel out, leaving us with 0.8127 times 10 to the 2. Notice that once again, the decimal is not between 1 and 10, so we have to move the decimal point, this time one place to the right. This will reduce the exponent by 1, and our result in scientific notation will be 8.127 times 10 to the first power. Notice that the exponent in this case is very small, which means the number could easily be expressed as a plain decimal. To do this, we move the decimal point one more place to the right to make the exponent equal to 0. Thus we can give a final result of 81.27. The Earth is 81.27 times as massive as the Moon. Adding and subtracting numbers is straightforward. First, move the decimal point in all the numbers so that they all have the same exponent. Then just add or subtract the decimal parts. The answer will have the same exponent as the numbers you started with. So, for example, the mass of a hydrogen atom is the mass of a proton plus the mass of an electron minus the binding energy of the atom expressed as a mass. So we have proton mass plus electron mass minus binding energy equals 1.6726219 times 10 to the minus 27 kilograms plus 9.109 times 10 to the minus 31 kilograms minus 2.424 times 10 to the minus 35 kilograms. We have to make all the exponents equal before we can add or subtract. So we move the decimal point 4 places to the left in the electron's mass and 8 places to the left in the binding energy to make all the exponents equal to negative 27, which gives us 1.6726219 times 10 to the minus 27 kilograms plus 0.00091109 times 10 to the minus 27 kilograms minus 0.00000002424 times 10 to the minus 27 kilograms. Now we just add and subtract the decimal parts and keep the exponent the same. So we get 1.672619 plus 0.0009109 minus 0.00000002424 equals 1.6735298756 times 10 to the minus 7 kilograms as the mass of the hydrogen atom. Next time we'll do more of these calculations, taking significant figures into account. For now, here are some practice problems for you to try. I'll put the answers at the top of the comments section so you can check your work. The Moon is 384,400,000 meters from the Earth on average. Express this in scientific notation. The Earth's radius is about 6.37 times 10 to the 6th meters, Express this as a decimal with no exponent. Hoover Dam's maximum electrical power output is 2 times 10 to the 9th power joules per second. How many joules of energy would it generate if it ran at this rate for an entire day, which is 8.64 times 10 to the 4th seconds? The International Space Station orbits at a speed of 7.66 times 10 to the 3 meters per second. How long does it take to complete one orbit, a distance of 4.26 times 10 to the 7 meters? The Earth's mass is 5.972 times 10 to the 24th kilograms, and the Moon's mass is 7.348 times 10 to the 22 kilograms. What is their mass combined? Remember, the answer is at the top of the comments section. If you want to see more videos like this, subscribe to my channel, or click on the link to the whole Project Physics course, or to the next video in this series, which is on keeping track of significant figures in our calculations, so that we know how precise our answers are. As always, if you have any questions or concerns, let me know in the comments. Until then, class dismissed.